Hello everyone, let's do one more example of finding the extreme values of a function on a given curve using the method known as the method of Lagrange multipliers. So here we have a curve given by x times y equals 1. Let's look at what that curve is. If I solve for y, I get that this is the curve 1 over x, which is a hyperbola. So what we call a square hyperbola, like that. And so it does go infinitely in every direction. It just goes all the way to infinity, infinity, infinity. So let's see what are the possible values for this function on that hyperbola. Let's look at first what the method of Lagrange multipliers tells me is that I have to make the gradient of f and the gradient of g. In this case, let's write this as g of x comma y. That's x times y equals 1. So g is x times y. We have to make those gradients be parallel. So let's first compute the gradients. So the gradient of f will be the partial derivative with respect to x, comma, the partial derivative with respect to y. And that is 2x, comma, 2y. And the gradient with respect to the gradient of g will be the partial with respect to x, which gives me y, and the partial with respect to y will give me x. And I have to set this up to be a system such that, well, I want this to be lambda times y and this to be lambda times x. So that gives me two conditions. 2x equals y times lambda, and 2y is x times lambda. And remember that they still have to satisfy the formula for the graph of g. Okay, so what can we do next is that, well, first of all, I can see what happens if y is 0. So I want to solve for lambda, so I want to divide by y, but if I want to divide by y, I have to make sure that y is non-zero. If y is 0, that would imply that x times y is 0. So there's no points with y equals 0. You can see it from the graph that at y equals 0, there are no points. So that means that there is, if x and y is on the graph that we're looking for, then y is non-zero and x is actually non-zero also. So I can divide by y here to solve for lambda. So I get that lambda is 2x divided by y, but also from the second equation here, if I solve for lambda, I get that lambda is 2y divided by x, and I can set them equal to x divided by y as 2y divided by x, which means that 2x squared is 2y squared, and that means that x squared is y squared, or that x is plus or minus y. What we have found is that x is plus or minus y, and we have to have points on x times y equals 1. So let me write those conditions here. We have that x is plus or minus y, and that x times y is equal to 1. That's where there might be critical points for the values of this function. So what are those points? If I plug in x in here, what I get is that plus or minus y times y is equal to 1, or that y plus or minus y squared is equal to 1. Minus y squared is negative, so it has to be that y squared is equal to 1, which implies that y is plus or minus 1. And since x is plus or minus y, we get also that x is plus or minus 1, but they have to be on the parabola or in the hyperbola x times y equals 1. So either x is 1 and y is 1, or x is minus 1 and y is also minus 1, so that their product is 1. So these 2 points are the critical points for that function on that graph. Let's see where those points are. So if I graph again my hyperbola, those points are in here and in here. So the point 1, 1 and the point minus 1, minus 1 is where there might be critical points. Let's see what the value is. So what is the value at those critical points? The value is f of 1, 1. Now here's my function f. So evaluate at 1, 1, and I get 1 squared plus 1 squared is 2. And the value at minus 1 is minus 1 squared plus minus 1 squared, which is also 2. So a critical value is of 2, and I have to decide if that is a minimum or a maximum. So how do I decide that? Well, I can do, for example, I can look at the values at other points. So what happens, for example, when x is 2 in that hyperbola, y would be 1 over 2. So at the point 2, 1/2, I get 2 squared plus a half squared. That's 4 plus a fourth, which is 17 over 4, which is definitely bigger than 2. And so that means that this value we found must be a global minimum. And since there are no other critical points, it must mean that there is no global maximum. The growth of the function, just as it goes in these directions to infinity, those values actually just grow to infinity. Let's see that. So if I actually solve for y, y has to be 1 over x on that graph, and then f of x 1 over x would be x squared plus 1 over x squared, which is x squared plus 1 over x squared. And this goes to infinity as x goes to infinity. So there is no global max. It just, the values are unbounded, but there is a global min, and that is the value we found using the Lagrange multipliers.